In this session, we're going to look at another fundamental class of collections, associative maps. Maps are special in Scala in the sense that they're both iterables and functions. We're going to explore the fundamental operations on maps and are going to apply them to a somewhat larger example. Another fundamental collection type in Scala is the map. Maps have two type parameters. One represents the key of the map and the other the value of the map. So it's essentially a data structure that associates key of the key type with values of the value type. Here are two examples. The first is a map of Roman numerals that associates strings I, V, X with the numeric values 1, 5, and 10. And the other is a map of countries which associates countries with their capitals. So let's see this in the worksheet. If I evaluate this, then what I get is two immutable map, the first from char to int, the second from string to string. And they have the values that I have entered into them. So the first map that I have defined would be of type map of string int. It associates an int value with a string key, and the second map would be of type map string to string. It associates a string representing a country with a string representing its capital. So maps are iterables. But in fact, maps are also functions, and that's because the class map key and value also extends the function type from keys to values. That means maps can be used everywhere functions can. In particular, maps can be applied to some arguments. So for instance, capital of country of US is a well-formed application, looks like a function call, but maps are function, so that would give us back Washington. But what would happen if we applied the function to a value that is not a key in the map? So for instance, capital of country Andorra. Well, let's try out. So what we get is, not surprising, an exception. It reads, no such element exception. The key Andorra was not found in the map. So what can we do to query a map without knowing whether it contains a given key or not? In fact, what we do here is, instead of having a simple function application, we can call a get method on the map. So if we do that, then what we get here is a so-called option value, and it reads none. So it would say, well, it hasn't found anything that matches Andorra. Whereas if we wrote, say, capital of country get US, we would get another option value which now read sum of Washington. So it's time to have a closer look at what these option values are. So in fact, option is another standard type in the Scala libraries. Here is its complete definition. Option is a trait. It has a type parameter, and there is one case class and one object that both extend it. So the case class is called sum, and it takes a value, and it's an extension of option A, and none extends option of nothing. So that means that an option value can be one of two things. It can be a none, which means nothing was found, or it can be a sum of x, where x is of type A here, and that means that something was found, and the thing that was found is the x here. Since options are defined as case classes, they can be decomposed using pattern matching. So if we wanted, let's say, to show the capital of a country without throwing a key not found exception, we could do something like this. We could get the country from the map capital of country, and then we could match the resulting option value. If it's some capital, we return the capital. If it's none, we return a string called missing data. And then if we do show capital of US, we would get back Washington, whereas if we did show capital of Andorra, we would get back missing data. Options also support quite a few operations of the other collections. In particular, they support map, flat map, and filter, so you can run 4 expressions over them, and I invite you to play with them and try out what you can do with them. For the examples that follow, we need 2 more operations on collections that both have analogs in queries. In SQL, these operations would be called group by and order by. Order by orders the element of a collection according to some criterion. That can be expressed in the Scala libraries with methods called sort with or sorted. So let's say we have a list of fruit here, and we want to sort it such that fruit with shorter names appear before fruit with longer names. So that we could write fruit sort with, and then our criterion is that the length of the first fruit must be smaller than the length of the second fruit. So that's would lead to the following result: pear, apple, orange, and pineapple. Or we could just sort a collection with the natural ordering, that's called sorted. Natural ordering here is lexicographic, so that would lead to the list that you see here. The other operation I want to cover is group by, which is directly available on Scala collections. What it does is that it partitions a collection into a map of collections according to some discriminator function. That's best seen by an example. So let's take my fruit list and let's group it by head. So head would be the character that appears first in each of these strings. So what that gives me is a map that associates each head character, so P, A, and O, that's the 3, with in turn a list of all those fruit that have that character as their head. So P would now map to list of pear and pineapple, A would map to list of apple, and O would map to list of orange. So let's do a more involved example using maps. What I want to do is look at polynomials. A polynomial can be seen as a map from exponents to coefficients. For example, the polynomial x to the cube minus 2x plus 5 could be represented with the map that says at exponent 0 we have a 5, at exponent 1 we have a minus 2, and exponent 3 we have a 1. Based on this observation, let's design a class polynom that represents polynomials as maps. So what I have here is a new worksheet. I've already given the rough framework of this class of polynomials. So I would say each polynomial should take as a parameter and field a map from exponent int to coefficient double. And what I want to implement is a plus operation on polynomial. So let's turn to that. Could I add, let's say, 2 polynomials like this one here and this one here? So what we need to do is we need to merge coefficients that have the same exponent. So what we would expect here is a polynomial where we said 0 was mapped to 3, 1 was mapped to 2, 3 was mapped to the sum of 4 and 7, so that would be 11, and 5 was mapped to 6.2. So how can I achieve that? Well, one idea would be I take one of the maps and then I add the adjusted coefficient of each of the second maps to it. Adding means replacing the binding of the same coefficient in the left map. So to define addition of 2 polynomials, what I can do is I can take the first map and try to add all the elements of the second map to it. Let's see how I would do that. Take the first map, so that's terms. Add, I will try to achieve with concatenation. So I would take the terms of the other, and that would give me a new map, and I just have to wrap that in a polygon. Let's see what that would give. Well, not much yet, because my map doesn't really print very well. You just get the default output which just says it's a polynomial. So maybe let's work first on a good 2-string function of polynomial. We'll get back to addition afterwards. So to turn a polynomial into a string, what could I do? Well, one thing to do it is I can take all the terms that I have, and I convert each term into a nice expression with coefficient and exponent. So let's try to do that. I would have a for expression that takes the exponent and coefficient of each term in my terms list, and it would yield the coefficient followed by an x, that's my variable, followed by an up arrow representing exponent, followed by the exponent. And then I just have to concatenate all these elements together with a plus in the middle. So let's see how we're doing. Now we get something nicer. We get polynomials that we can read here. One thing we notice is that they are not yet sorted. They can appear in any order. For instance, the last one starts 1, 3, 5, 0. So we would like to have the terms in sorted order, with the highest coming first. So one idea here would be to say, well, take the terms, convert them to a list, because we need a sequence to sort them, sort them, so that goes from small to large, and reverse them in the end. So terms to list, sorted, reverse. Let's see what we get now. So now the things are nicely sorted, 5, 3, 1, 0. On the other hand, unfortunately, the result is far from being correct. Let's see what we did here. We have the first exponent from the first polynomial, that's fine. Then we have the cube term from the second polynomial, but in fact what we really need is the sum of the two cube terms in both polynomials. So what happened here is, with the operation plus plus, what we did really was just to essentially superimpose the terms of the other polynomial on top of this one. So if the left polynomial didn't have a term with a given exponent, that was okay. We would just take the term of others and it would be correct. But if it did have a term with the same polynomial, that term would be lost. What we need to do instead is have a function that in that case would add together the two coefficients. So how would we go about doing that? Well, the best way to do it almost always in functional programming is break it out into its own simple function. So we would say, well, let's go over the other terms and essentially map, call this adjust for adjust the coefficient. And that's a function we'll have to define. So we define adjust, and that takes a term, so that would be a term, and that's a pair of an int and a double. And we wanted to return the adjusted term, again a pair of an int of a double. So what do we need to do here? Well, we need to see whether the key of the term is already in the left map. So let's maybe pull out the key. So we say val exponent coefficient equals term. So now we have nicely the two sides in variables each by themselves. So what we must do now is find out whether the existing terms have already a coefficient that matches exponents. So let's do that. We say terms get exponent match. In the case where this is yields some coefficient 1, say, we return a pair or a binding that goes from the exponent to coefficient plus coefficient 1. And if there was nothing in the map, then we return the binding that goes from exponent to just the coefficient of the second map. What we did here is that the arrow and the plus have the same precedence, but we need to put the parentheses here like that, because of course we want to have the exponent map to the sum of the two coefficients. Okay, so now what we see is that the cube coefficient here reads 11. That's what we need. Good, so we're done with the addition, but it felt kind of heavyweight to do all this computation. Is there a simpler way? Well, indeed there is. So far, maps were always partial functions. Applying a map to a key value could lead to an exception if the key was not stored in the map. What if we could make maps total functions that would never fail but would give us back some default value if the key wasn't found? There's an operation that does that. It's called withDefaultValue, and that operation turns a map into a total function. So if we had written, for instance, cap1 equals capital of country with default value unknown, then we could have safely applied cap1 to Andorra and we would have gotten back unknown, because that's the default value. No more key not found exceptions. So let's apply this technique to our worksheet. What I will do is that I will, instead of having a terms field, I just call this a terms 0 parameter, and I will create a new field, terms, which is terms 0 with default value 0.0. So now all my polynomials have maps that have a default value. We can try to test that by calling p1, first polynomial, dot terms of some exponent that's missing, and we would get back a 0, 0 instead of the exception that we would have expected to see before. With the new map with default values, we can greatly simplify the adjust function. We need no longer test whether terms contains a given exponent or not. We can delete all that and replace it with a simple return expression that says, well, given the exponent, I associate it with the coefficient of my second map plus whatever the coefficient was in my first map, and that would be just terms of exponent. And I get back the same polynomials as before. So you see there's great power in working with maps that have default values. Often the code that deals with them can be greatly simplified. So far so good. But there's still something slightly unnice about that, and that's the way we had to create polygons. We wrote new poly, and then we had to pass a map into each polygon. Is there a nicer way that ideally would let us avoid the intermediary data structure? So ideally we could just write poly of 1 to 20, 3 to 40, 5 to 62. Well, for the moment, of course, that doesn't work because poly takes a map as parameters, and here we have what? Well, we have 3 pairs of int and double elements. The problem, of course, is that we could have 3, but we could have also 4 or any other number of pairs that we pass as parameters to poly. So we need a way to pass a varying number of parameters to the same function. In fact, Scala does offer that ability with its use of repeated parameters. So let's show this with an auxiliary constructor in class poly. We haven't seen them since week 3, so it's a good time to refresh. So the auxiliary constructor would take a sequence of bindings. Each binding is a pair of int and double, and the fact that it's a sequence is expressed by the star here. So the star means it's a repeated parameter, and that means we can pass an arbitrary number of concrete arguments for this formal parameter here. Internally, all the arguments are represented as a sequence. So that means that if we call now the primary constructor, what we can pass along as arguments is simply the sequence converted to a map. So if we do that, then the spreadsheet compiles again and we get the same polynomials as before. We can also get rid of the map, of course, in the other calls to polynomial. So here's the final implementation of polynomials. As an exercise, I would like you to tweak this a little bit. So here we have expressed the addition operation with a concatenation of the terms of the two maps where the second terms were adjusted. It is also possible to express the same operation with a fold left. And I'd like you to do that in the exercise. So what I'd like you to do is write plus as follows. It takes another polynomial and creates a new polynomial where you apply a fold left operation to the other terms as a collection, and you have to figure out what the unit element here is, with an operation add term as the combining operation. And again, add term I would like you to implement. Once you've done that, you are able to answer the following question: which of the two versions do you believe is more efficient? The version using plus plus or the version using fold left? So let's see how we would solve this problem in the worksheet here. So I'm going to start to work on the implementation of plus. We said it should have been other terms, fold left, with some zero element. So what would that be? Well, I'm going to argue it must be terms, because if other terms is empty, then clearly we want to return terms. So the zero element will be terms here. And the combining operation will be called add term. So I have to work on this one now. So add term takes now the zero element, so that's terms, a map of int and double. And it takes a term that's taken from the other terms list here, which is a pair of int of double, and again it returns another map of int and double. So what would its implementation be? Well, in fact, we don't need to change much from what it was. So all we need to do is that instead of returning a single binding, we immediately add this binding to the given terms map. So we would return terms plus the binding that we've seen here. And that does it, so everything compiles and we get the same results as before. So now to answer the question, which of the two versions is more efficient? So I would argue the one with fold left is more efficient, because what happens here is that each of these bindings will be immediately added to our terms map, so we build up the result directly. Whereas before we would create another list of terms that contained the adjusted terms, and then we would concatenate this list to the original one. So the version with fold left avoids this creation of the intermediate list data structure. So in that sense, it looks like it's more efficient. So I would vote here for fold left.